regulators. In particular, we'll be looking at 2 voltage regulators that you'll be investigating during this course. Many electronic circuits operate on a stable or require a stable DC voltage. So for example, if we have our electronic circuit which may have a varying load to it, so the current requirement varies, what we do not want is we don't want that varying current to make the input voltage increase or decrease. By the same token, if, for example, we're connected to some sort of generating system, like a car, we don't want our voltage going into our circuit to change. So we need to somehow regulate it. So what we have, for example, here, even if our current changes, or current requirement of our circuit changes, we want our input voltage to remain constant. And to do that, we employ what is known as a voltage regulator. The simplest form of voltage regulator that we're going to be investigating is called the Zener diode, invented by a man named Mr. Zener. And there's a couple of symbols that you might see. One looks like this and one looks like this. You can see that they are pretty much the same as a diode, except for this little bit on the end of the cathode. And once again, conventional current flow flows in the direction of the arrow. Zener diodes come in various shapes and sizes. Often the small ones are encapsulated in glass. They may have a number written on them, and in this case it would be a 6.2 volt Zener. They may also just have a code number, which we would have to look up to see what its rating is. They will also have a band around one end to mark the cathode. Unlike a standard diode, which we all operates normally as a blocking, we can operate forward or reverse. A Zener diode is only ever operated in the reverse condition. We never use a Zener as a normal blocking diode. And Zeners are manufactured so that their breakdown voltage is a very specific and exact value, like 3.2 or 6.5, 9 volts, 12.2 or something like that. Very, very specific. Where a Zener diode differs markedly from a standard diode is the breakdown region. And in a Zener diode, once you get into the breakdown region, instead of it totally just breaking down and being destroyed, there is a small area where the reverse voltage can increase and decrease, and our diode will actually survive that breakdown point. And so we have the symbol delta, small letter d, and capital D in the Greek alphabet for delta. So little d means a small change. In this case, small change in the Zener voltage of reverse voltage makes a large change in the Zener current. We can, however, push our Zeners too far, and they are still sensitive to current, and there is a maximum current which they can draw, which will be specified on their spec sheets, and so we have to be careful that we don't go past there. They'll heat up too much and be destroyed. But we can operate in this range where they can recover from the breakdown in the breakdown region. So, as an example of a circuit where Zener might be used, is, let's say we have this example where we have a 12 volt circuit. We want an exact 9 volts out, so we have a 9 volt Zener. So if we have 12 volts input and 9 volts across here, then we must have 3 volts dropped across there. We arrange the circuit so that, let's say for example, our voltage increases to 13 volts. Our output will stay constant at 9 volts. The extra voltage would be dropped across this resistor. So how is this achieved? Providing our current doesn't fall below the minimum value, and we normally have a area here we call the knee. So as long as we get our current past the knee into its operating range, the current through the Zener can vary up and down, but its voltage will stay relatively constant. It will move a little bit, but it will be relatively constant. Let's say 6.2 to 6.3 or 4 volts, which isn't very much considering that the current may change from 20 to 40 or 50 milliamps, a big change in current. Now, to get our Zener to operate effectively, we get it past the knee down into its operating range to start with. And to do that, we make an assumption. We are, when we doing the calculations for a circuit, we will assume that the Zener in the initial stages, we want it to draw about 10% of whatever the load value is. So in this case, so what we're going to do here is we're going to use these figures here. If we have a 7.5 volt Zener, which is capable of, or is rated at 1000 milliwatts or 1 watt, and we connect it to a 12 volt supply, what's the maximum current that we can put through the Zener without going over our 1 watt rating? So our I is equal to P over V. So we have 1000 milliwatts, 7.5 volts across the Zener. Therefore, our maximum current that the Zener can handle is 133 milliamps. What value of resistor would be needed, or the minimum value that we can have here to make sure that our current doesn't go above that? Well, once again, so what is the voltage across the resistor? If we had 12 volts in, 7.5 volts across our diode, that would give us 4.5 volts across the resistor. And the maximum current is 133 milliamps. So the value of the resistor, we can't go below 33.8 ohms. Otherwise, we know we're going to destroy the Zener. Now, to get our Zener into the operating range, past the knee, what we do is we get it to, we assume 10% of the load current we'll put through the Zener. So when it's just in its normal operating mode, whatever the load current is, we take 10% of that and put it through the Zener. So our total current is 110% of the load current. So in this case, if we have a 7.5 volt Zener and our load resistance is 100 ohms, we will have 75 milliamps flowing through the load, plus 10% we're going to put through the Zener to get it past its knee into its operating range. So our total current in this situation is going to be 82.5 milliamps will be flowing in the circuit. So if we have 82.5 maximum current, what is the resistance of our RS going to be? So we have 12 volts input, we have 7.5 volts dropped across the Zener. Therefore, we have, what do we have left? We have 4.5 volts left across to go across our resistor, divided by our maximum current, 82.5, we have 55 ohm resistor. And is that below our, what did we calculate for our minimum value of resistor? Go back to here, 33.8. No, so we haven't gone below our minimum value. So our resistor will be 55 ohms in this circuit. So we have 82.5 milliamps maximum current, 55 ohm resistor. What is the power rating of that resistor? Because remember, resistors have two values, their ohms value and their power dissipation value. So power is equal to V squared over R, so 12 squared. And what we assume here is that the worst case scenario, if the load gets shorted out, in other words, a direct short across anywhere across this line to earth or to negative, means the whole 12 volts is going to be across that resistor. This is the worst thing that could happen to that resistor. So we assume 12 volts across the resistor. It's valued at 55 ohms, 12 squared divided by 55, 2.6 watts. Now we don't have a 2.6 watt resistor. Resistors come in quarter, half, 1, 2, and 5 watt, 10 watt. values. So we would, to be safe, we would use a 5-watt resistor there as the minimum value of its wattage rating, power rating. So that's the resistor taken care of, 55 ohms at 2.6 watts or 5 watts we'll go up to. Now, what's the worst thing that could happen to the Zener? The worst thing that could happen to the Zener is that the load gets disconnected and all the current has to go through the Zener. In that case, we're going to use this calculation, the power requirement of the Zener, or the power dissipation of the Zener in the worst case would be its voltage, 7.5 volts, multiplied by the entire current. So 7.5 times 82.5 would be 0.6 of a watt, or roundabout. Now, Zeners don't come in 0.6, they normally come in half, 1 and 2 watt values, so we would need to use a 1 watt or a 2 watt Zener. In this case, to be 1 watt would be ample. Now, Zeners don't always work as voltage regulators just by themselves. We can also use other electronic components, and we use the fact that a Zener has a stable voltage across it. So, for example, if this was a 7.5 volt Zener, it's going to, this part of the circuit works exactly the same as the previous circuit. But in this case, instead of the Zener having to take extra current, or we can actually protect it by putting a high current device like some form of transistor in series with the load, and that the Zener will just control that device. Now, we're not going to build the circuit, but if you see it, you need to be able to recognize it as being called a series regulator, and the Zener controls the transistor. The second type of voltage regulator we're going to be investigating on this course is called a 3-terminal regulator. It's called a 3-terminal regulator because it's got 3 terminals. Unlike a Zener diode or a resistor or a capacitor that's only got 2 legs, this one's got 3 legs. So its legs are its input, its output, and a ground terminal. And it's connected in a circuit like this. Our input leg, our input comes in, our output goes out, and we've got a ground, and there's often a couple of other small components around it, small values of capacitor to help it work. They're not always necessary. Note that this is not the filter capacitor, it's a much smaller value, and it's designed to assist it with high frequency switching should transient voltages occur. All right, so 3-terminal regulator. You may see it without these resistors, you may see it with them. You notice back there that the 3-terminal regulator was called a 7/8 something or other. We'll go back to where it was. No, it wasn't. Can't see it on there. Oh, here it is, 7805. That tells us it's a 5-volt regulator. Its output is 5 volts no matter what its input is, and the 7/8 is just the series number. And 7/8 means it's a positive regulator. We can have negative regulators that regulate from 0 down if we want negative voltages, and they would be 7/9 series. But the 7805 is a 5-volt regulator, 7812 is a 12-volt regulator. Now, the advantage, okay, the 7809 is a negative regulator. We won't actually be investigating that. We'll just be looking at the 7/8 series, a positive regulator. And they have, just by themselves, they can handle up to 1 amp of current. The advantages of 3-terminal regulator is that they're very easy to use. We don't have to do calculations like we do with the Zener regulator. It simplifies power supply design. They're small in size. They're quite inexpensive these days. They're very versatile. They have inbuilt features like if they get too hot, they'll shut down. If you try and drag too much current out of them, they won't let you do that. They'll shut down as well. So they're very versatile and robust little devices. Despite the fact that they're quite complicated, there's something like 1,000 PN junctions inside one of those little regulators. The capacitors that were around them are required if the regulator is not particularly close to the powers the main filter, we can put these extra ones around. And also, if it's going to be in a noisy, electronically noisy environment, we can put extra capacitors around there as well to help reduce any noise. The main difference, or the way they work, is, for example, the voltage in, for them to work, has to be 2 or 3 volts above the voltage out. So, for example, if we have 12 volts in with a bit of a ripple on it, and that ripple is sort of plus and minus 1 volt, then we would need, that would only supply like a 9-volt regulator. So we need normally between 2 and 3 volts more in than we expect to get, or we need to get out for this to work properly. We can also use 3-terminal regulators as a variable regulator. There is a specific one called the LM317, and it's a variable regulator. Operates almost exactly the same as a 3-terminal regulator, except instead of the common going to ground, it can go between a couple of resistors, and we can make one of these resistors, normally this one, variable, and we can change the output. And for example, a LM317, if you connected that to a say a 20 or 18 volt input, we could then vary its output from 1 up to about 15 or 16 volts. There's a lot of information about these and how they're used. Here's a reference that you might find quite handy. And that's regulators in